Hey everybody, I'd like to introduce Gunnar Luderer from Potsdam Institute on climate impact research. He's been looking at like the global aspects of decarbonizing the world and the pathways for, well, society to respond to climate change. So yeah, welcome Gunnar.
Thanks, Greg. Yeah, it's a great pleasure to be there and talk to you and present our work on modeling energy transition pathways to climate neutrality. I did bring a few slides, so let me jump in. So the overview is that I would first give a bit of background about the state of play regarding climate crisis and what that needs and why we have to go to net zero energy systems. I will also want to talk about the shifts in the economics of energy. There's a lot going on regarding technology and economics, etc. Then I will talk about the methods that we use, so-called integrated assessment modeling. Then we can look into basic characteristics of net zero energy systems and look at stuff like direct electrification versus indirect electrification, decarbonization bottlenecks, so sectors that are particularly difficult to wean away from fossils, then near-term priorities like avoiding carbon lock-ins and scaling up clean technologies. Okay, so let me jump in. So where do we stand with regards to climate change? This is like an updated time series of global average temperature as observed since 1967. What's noteworthy about this is that last year, actually 2024, and that's a consensus across different data products, was the first year that was actually above 1.5 degrees relative to the pre-industrial reference. But maybe what's even more important is that 2015 through 2024 are the 10 warmest years on record. So that means every single one of these 10 years, 2015 and 2024, was hotter than the 150 years that we have on record before, and likely even than the last 100,000 years, where we have some paleo data to reconstruct temperature records. So that's quite dramatic. How important or how relevant this all is becomes even more clear if we go further back in time. So this is a long-term reconstruction of global mean temperature dating back until 2000 years before Christ. By 2000 years before Christ, that's because that's roughly the maximum of the last ice age with the maximum extent. So what's noteworthy about this temperature, about this temperature timeline is that this recent warming that we've seen, it happens in a blink compared to these historical timescales. So we've seen lots of warming and a much higher warming rate than historical. And the other thing is that this last ice age was only a few degrees colder. There's some uncertainty about this. It might be 3 degrees, it might be 5 degrees colder than the pre-industrial temperature level. But if we consider that the face of the Earth was so dramatically different during the ice age, with major ice sheets covering both northern Europe all the way going to Berlin, where I currently live, or also more than half of the North American continent, for example, shaping the Great Lakes under 2,000 meter thick layer of ice, it becomes quite clear that a couple of degrees warmer will have equally dramatic effects on the planet. So what we know from climate science is that small changes in global mean temperature can result in large-scale system changes, and that's something that we call tipping element. The science has identified a number of these tipping elements. I will not go through all individual ones of them, but just a few examples. So the Western Arctic ice sheet is one of them, and this color coding here indicates kind of the level of risk. And already at 1.5 to 2 degrees, we're getting into an area where these ice sheets for Western Arctic and here Greenland are starting to become, the risk of them becoming unstable is increasing. And that's quite important because there is 5 meter worth of sea level rise in the Western Arctic ice sheet and 7 meters worth of sea level rise in the Greenland ice sheet. So if these ice sheets start to melt, that is quite dramatic for coastal areas. For example, Florida, for example, New York City, which is all quite low lying. And then, of course, looking to the future, there are different futures, and it's in our hands. So, like what we in climate science use to classify these different futures is the level of radiative forcing going to the future. So, like the strength of the greenhouse effect. And if we are serious about decarbonizing, we can limit this radiative forcing to 2.6 watts per square meter. That's kind of this green line, implying well below 2 degrees stabilization. And on the other hand, in the worst case scenario, maybe we are not in anymore for this very worst case scenario. It could be in the very long term up to 8 degrees of warming.
So question,
sure.
The like our nonlinear effects that accelerate climate change because you hit the tripping point?
Actually, like there are nonlinear effects, and those affect tipping points. They affect, for example, these ice sheets. Because it warms, ice sheets melt, and then kind of the elevation of the Greenland ice sheet goes down, which kind of makes it like accelerates the melting. The extent to which there's kind of a self-enforcing element in the warming, that's not so clear. Like there are some things that are going on, for example, melting sea level, right? Like the ice around the North Pole will expose more of the relatively dark sea surface, so that's a positive feedback. But like usually when we talk about tipping points, it's not necessarily about kind of self-enforcing warming. It's more about like this change of state of large-scale Earth system elements.
Got it. Thank you.
Thanks for the question. So that was climate science. We can also look into economic aspects about climate change. There's a increasingly strong line of evidence from like economic climate research that shows a strong correlation between economic growth and warming based on a very large scale data sets. And what we learn from that is like with increasing fluctuations on warming level, or with stronger warming, there tends to be less economic growth. And extrapolating these effects into the future, we can estimate the amount of economic damages that result from global warming. And the latest estimates that's published in Nature come to a damage estimate of around 10 to 25% of global economic output by 2050, just because of the warming that's in the pipeline. If you go to a high emission scenario, which would imply warming by the end of the century of 3 to 6 degrees centigrade, these losses could be more than half of global economic output. And that's an increasingly robust line of evidence, and it really matters. Another way of looking at this is that we can also estimate the amount of economic damage per ton of CO2 that we emit. This is regularly done. The most recent estimate by the US EPA that was performed in 2023 came to the conclusion that this so-called social cost of carbon, so this additional damage for each ton of CO2 emitted, might be around $200 per ton of CO2. That's very significant. Last point about the climate physics component. There's one very important finding from the climate sciences, and that is that basically there's a quasi-proportionality between cumulative CO2 emissions, so the total amount of CO2 emitted by humans since the beginning of the industrialization, and warming. And that's illustrated here, kind of based on historic records, but then also based on model estimates of these different emission futures going forward. And this proportionality is very important, like has very important implications for climate policy. It does mean that ultimately there's a finite residual CO2 budget. So for example, if you want to limit warming to 1.5 degrees, there is roughly 300 gigatons of CO2 left. If you want to limit warming to 2 degrees, it's 800 gigatons of CO2 left. And these are relatively small budgets if you consider that current emissions sit at roughly 40 gigatons CO2 per year. So for 1.5, that's basically 7 years of current emissions that we can still afford to emit within that budget. And of course, if we only have a limited amount of CO2 that we can still emit as humanity, that means that we have to go to net zero CO2 emissions to stop global warming, to prevent further warming to come into the pipeline.
So, question: there's warming and there's damages. So, yes. So it sounds like it doesn't matter when for warming. It doesn't matter exactly when a particular ton was emitted, but first of all, is that correct? And also to what extent do aggregated damages from a given emission depend on the year when it happened?
Well, the way you can think of it is like that every ton of CO2 that you emit more or less instantaneously results in an increment in warming. Mm-hmm. And that results in damages. What you usually do in damage estimates is that we discount these damages that are further in the future, discounted to present. So you kind of put more weight on the near-term damages than on the longer-term damages. That's why timing does play a bit of a role, even though the warming response to a ton of CO2 is almost constant over time. The other fact is, of course, that also economies tend to grow, and therefore there tends to be more damages in the future than in present, just because you have kind of more, a greater economic system that is affected by that damage.
Got it. And then now, in terms of economic growth, this is a difficult one because you can argue that if you pollute like crazy, then you'll have excellent economic growth, and that baseline can actually be very rich. And if you were to avoid warming and save nature, then, well, you're going to be less rich because you didn't pollute so much. So how do you compare those two scenarios?
Yeah, that's a great question. Like, that's something that we call cost-benefit analysis. So you can ask yourself, what does it cost to reduce emissions in terms of in GDP terms? And maybe going back to this earlier slide, actually there we have it. So these costs of limiting warming in line with the Paris climate targets, that's the green line. And that's pretty small compared to these economic damages that we have. So we're talking about roughly a factor of 10, right? So that you have between mitigation costs, so cost of reducing emissions, compared to these climate damages. So we are nowhere near these 20% losses from climate change mitigation. So reducing emissions is nowhere near as costly as these damages are.
Is there like a dollar estimate of like in terms of a fraction of GDP? Is there an absolute number on how many dollars that might cost?
Say that again.
Scale? So to get a sense of scale, how expensive would the decarbonization transition be?
So global numbers, what I know off the top of my head is something that we regularly look at, and that's a marginal abatement cost. So like, what does it cost to have like one extra unit of CO2 avoided? And there's lots of very cheap stuff. Like a lot of that is even negative cost by now. And I'll talk about this later, like renewable deployment, solar, wind in most world regions is really close to zero, sometimes negative, often actually negative. In other regions, it might be slightly positive. Then also electric cars are getting very cheap. So it's like, it might still be a positive abatement cost, but as a matter of 5 or 10 years, it will be cheaper on a kind of life cycle basis to have an electric car compared to a combustion engine. So again, we are kind of in approaching negative mitigation cost terrain. And then there are a few things that are very expensive. I'll talk about this, and that's, for example, switching to synthetic fuels, renewable fuels for aviation. That tends to be very expensive. So there we would be talking about hundreds of dollars per ton of CO2 as a mitigation cost. But that tends to be a small segment. Excellent. Okay, so let me proceed. We talked about the final budget and the need to get to net zero, because we have this final remaining amount of CO2 that we can work with if we want to limit warming in line with these targets. So kind of looking under the hood, going towards the methods. So the types of modeling approaches that we use to assess climate change in general and climate change mitigation, so reducing emissions, avoiding climate change, more specifically, are called integrated assessment models. We, in my lab, are developing and operating the Remind integrated assessment model, which is one of the 5 big integrated assessment models that I used, for example, for global climate assessments. So what Remind is composed of, there's one core module about the macroeconomy. That's a slightly complicated graph, but to give you like a rough idea what this is about, we can describe the economy in terms of the economic output here in the center. That economic output can either be used to invest for further productivity. It's like on the regional level, there's also trade. And part of this economic output is also available for private consumption by households. The way this system is formulated is as an optimization problem where we maximize the welfare, which is kind of a function defined by this private consumption by households over the time horizon that we consider, typically until 2100. And that's a well-established method under certain assumptions. It emulates quite well the equilibrium that comes from from a market economy. This optimization problem to maximize that welfare is then subject to certain constraints. For example, that you can spend your economic output only once, either on investment or on consumption, or on exporting goods. And then the other part is there's a production function. So the amount of economic output that you produce depends on input factors like capital, like labor, but then also energy-related input factors. And that is where the system then connects to like quite detailed energy system, where things are represented like the industrial sector that produces goods, very important for the economy. Also the transport sector, both goods transport and passenger transport. The building system, which requires energy for heating, for cooling, but then also like all these commercial activities, data centers, etc., are also part of this sector representation. And then, of course, we have the energy supply system, which is about the conversion of primary energy resources for end use in these different sectors. Then there's one more box, and this is about novel technologies to get CO2 either outside of the suck it out of the atmosphere and sequester it, or what we call carbon capture and storage, so to use the CO2 from industrial processes, capture it and store it geologically. So this is the main part of the model. It can then be connected to other models. For example, we have a reduced form climate model that can give us projections, that can translate the emissions from the energy system to projections about climate change. We have a module that calculates damages based on these methods that I showed earlier, these econometric or like statistical analysis. We also have a module where we can translate different energy system activities into other environmental impacts, where we can study things like material use, like land occupation, and other things that matter from a sustainability perspective. Also quite important, our model can be coupled to an agriculture and land use model. That's quite important because there are also significant emissions from agriculture and from forestry, and also this agriculture system matters for the provision of bioenergy as a substitute for fossil energy in the energy system. So Remind has 12 world regions. We also have a version where we have break down the EU in kind of 10 sub-regions. So overall, we're working with 21 regions. The time horizon is typically until 2100, as I said before. So we cover CO2, methane, nitrous oxide, and fluorinated gases. So these are the most important greenhouse gases to understand warming. And then what's a very important feature of Remind, and that's quite unique, compared to other integrated assessment models that we have set up the system that we can take into account non-linearities such as technological learning, or the integration of variable renewable energy, or also like in these economic production functions, there are lots of relevant non-linearities that we cover. So this is this is all integrated in Remind, which means that on the numerical side we are solving a non-linear optimization problem with roughly 50,000 degrees of freedom. In the system, we have some tricks how we deal with that, so we don't solve all world regions at once, but solve these regions individually, and then iterate to make the computation performance better. But it's a rather large-scale optimization problem that we look at here.
So,
okay,
just from a modeling perspective.
Sure.
Should we be thinking of a big set of constraints where the people are presumably optimizing welfare and you're modeling them as welfare optimizers under the evolution of climate change and whatnot?
Exactly. So like actually the entire representation of the energy system, basically like from a modeling perspective, these are all additional equations that that are translated as constraints into the system. And then, for example, the climate policy comes in as a constraint on the remaining amount of CO2 that we can still emit. Another way of doing that's a possibility that we have, is that we put in an explicit tax on CO2 or methane into the system to represent such a policy intervention. But in the end, it's really like an optimization problem with a very large set of constraints that arise from these different properties of the energy balances and the energy system.
Got it. And so now, in terms of the resolution of the model and kind of the other modeling approaches for these things, do you incorporate like power grid modeling or global trade matrix kind of modeling, or is this kind of a coarser constraint-based system kind of model?
Right. So Remind is on the spatial side quite coarse, but we represent things like renewable integration based on reduced formulations that are derived from detailed grid modeling. And we now have an effort underway to couple like the Remind model explicitly with a continental scale power system model that really has hourly resolution of the power system. So that's quite exciting because like there are lots of interesting effects regarding renewables, regarding also electrification of transport, buildings, etc. So that's kind of the research frontier. We're quite excited about this because like none of the others, like it's really hard to do both global, both long-term, and then also go into these hourly and small-scale details that matter for some of the energy system. And we are quite close to managing to do that. So we have one kind of toy model where this works for Germany. Now we're working on doing this for Europe, and then the next step is to do this for all other world regions, like with an explicit power system model detail.
Right, and we should be thinking like hourly. That's the to what extent batteries are important for solar versus wind versus geothermal, which does not require batteries, right?
Exactly. So these effects matter, and like a key insight that we have from the grid modeling is short-term stuff. You can like short-term fluctuations are relatively easy to overcome. There's demand flexibility. Then batteries get increasingly cheap, so that doesn't matter too much. But the major challenge that remains is seasonal variation in supply and demand. And that's very region specific. Like for example, if you sit in California, things are quite okay because your system peak tends to occur in summer, and you also tend to have lots of PV power in summer. If you sit in Germany, our peak tends to be in winter for the heating, and maybe it might be the same for the Midwest if people switch to heat pumps. So you tend to need a lot of electricity in wintertime, and that doesn't correlate well with your cheap solar electricity supply. So we really have quite substantial differences in renewable integration challenges depending on the geographical context and the seasonality of the demand mostly. That's really what matters most.
Great, thank you very much.
Yeah, thanks for these great questions. Very much to the point. So yeah, let's jump in on the energy system. So this is just like one standard result. It's already a few years old, but I like the way that we displayed it here. So to understand what such a 1.5 degree scenario, and that's super ambitious, of course, what it looks like. This is one illustrative pathway. And yeah, it gives you an idea how net zero can be reached while minimizing residual fossil CO2 in line with this 1.5 degree target. So typically what we see in such scenarios is you need to halve emissions within 1 decade, roundabout. So that's the scale of the challenge. And then we have to go to net zero, and typically that's in the second half of the century. And there's some connection between those two. Like obviously, if you're slightly slower in your near-term emission reduction pace, you have to reach net zero sooner because there's only a limited amount of CO2 that we can still afford. And then what's also interesting is to look into the sectoral patterns. So like, for example, here, what sticks out is that the power sector accounts roughly for a third of global CO2 emissions here in orange. That's something where we can reduce emissions relatively quickly at relatively low cost. But then there are other sectors where things are more difficult, emission reductions, and that tend to be the demand sectors like non-electric energy demands in industry, buildings, and transport, and in particular things like freight, aviation, or heavy industry, steel making, cement making, chemicals. That tends to be more tricky and take longer to get emissions down there. And these remaining fossil emissions that we have here in the system, they are of course a key determinant of the question whether or not we can still reach the 1.5 or even 2 degree targets, and also of the scale of the green part here. And the green part here is about like what we call carbon dioxide removal. So technologies to get CO2 out of the atmosphere and underground. That can be something as simple as afforestation or enhancing the carbon content of soils, or it can be something quite sophisticated as direct air capture. So like really artificial trees that suck through atmospheric air and take out CO2. That's quite a challenge. So what helps, of course, is that we are in a world with lots of technological progress in the past. So just to kind of set the scene here, what we have seen in the last slightly more than 10 years is a quite drastic decrease in the cost of solar and wind power, roughly 90% cost reduction for solar photovoltaic power. Wind has seen roughly 70% reduction for offshore wind, and similar for onshore wind over the same period. So that's quite dramatic, and it matters because since a few years, for most world locations, we are in a regime where renewable power is now cheaper than fossil fuels for new built installations. The other interesting part is if we look at batteries, and that's of course a key technology for electrifying transport. Also, like similar, very steep cost reductions have been achieved. So roughly 80 to 90% cost reductions in the cost of battery packs, and that really matters because, like typically we say, around $150 per kilowatt hour is the threshold below which electric cars become competitive with combustion engine cars on a total cost of ownership, kind of a life cycle basis. On the other hand, if we look at kind of more conventional large-scale technologies that were hopefuls for climate change mitigation, such as nuclear power, we don't see big progress. In contrast, historically, the cost of nuclear power has increased, not decreased. And especially in Europe, there are a few examples where kind of new nuclear power stations are commissioned and built, and they tend to be even more expensive than the more recent than the data points that we have observed in the past. So nuclear is quite expensive, and it's hard to see it play a big role and compete with these increasingly cheap renewables.
So there's actually a
Sure.
question. Why? Because, so I'm thinking my comparison point is like renewables with long-term battery storage. I mean, best case scenario would be seasonal storage from summer to winter versus nuclear, which is just base load, burns all the time. That's its advantage. But then, yeah, there's this high cost thing. So what's stopping us?
Yeah, so like that's precisely the kind of calculus that the optimization models do. And the one benefit that nuclear has is that it can run baseload, but that's increasingly less interesting because you have this super cheap solar coming in. So even if you can run your nuclear power station 8,000 hours per year, like all 90% of the time, it only produces valuable electricity that can compete with renewables in wintertime. So that undermines the case. And in the end, what ends up cheaper is a combination of typically, it's really there's a geographical component to it, but in most geographies, what's cheaper is a combination of solar plus wind plus batteries. And then for maybe the last 5 or 10% of load that are difficult to cover, things like hydrogen turbines to overcome kind of what we call Dunkelflaute in German, like periods with little sun, little wind, and high demand. But that tends to be like 5 or 10%. Like I think Germany is a relatively difficult case, but really like these problem hours are not big enough to give a good enough of a business case to go for nuclear, given the high installation costs that we see.
So should we be thinking of solar and wind as being just heavily overbuilt so that even when there's not much sun, the amount of power we get is enormous, only adequate? Or should we be thinking like 6-month-long batteries that go from summer to winter?
No, it's most of it is really like batteries that work the diurnal cycle. And then maybe you can think of hydrogen as like a seasonal battery system. But it's really because batteries don't work on this very on these very long time scales. They are too expensive in terms of their storage reservoir size compared to hydrogen. Hydrogen is expensive kind of in the conversion of electricity to hydrogen, but it's cheap regarding the kind of terawatt hours of hydrogen that you need to store. So that's why hydrogen tends to be the favored option for seasonal storage. But the point is really like you really want to minimize the seasonal storage because it's expensive, and the way to do that is to smartly combine wind and solar. Like for example, in Europe, and I think most geographies tend to have more wind supply in wintertime, so it kind of nicely complements the solar supply, and you really need to balance the mix between the two, and that minimizes the amount of seasonal storage that you need. So like I said, a typical order of magnitude would be maybe 5% or 10% of your total electricity demand would need to be covered by seasonal storage.
Thank you.
And that's the expensive part, but everything else will be quite cheap.
That makes sense.
Excellent. So CCS is a technology that's actually not only for the power sector, but also, for example, for industrial processes, for cement, quite important. But what we saw is that actually the project pipeline declined for much of the last decade, and only recently we saw some new projects proposed. But it's really like we are at a very small scale. The red part here is operational CCS, 15 megatons. That's about a per mil of our total CO2 emissions. So that's still very, very small. And then finally, regarding bioenergy, which is a nice substitute to fossils because you can use it as a fuel. It's a hydrocarbon as well. But there are severe sustainability concerns, which means that the role of biomass will be limited by the amount that we can supply sustainably. And that might be like 5% or so of our total final energy demand. Okay, so what all these effects combine result into is a fundamental difference between electric and non-electric energy. And I brought a few result graphics that look like this. So what we typically look at here is different scenarios, a reference scenario. So that's just a continuation of current policies. And even without much, and then like more sets of scenarios. One with optimistic assumptions about renewables and electrification technologies, and one with more optimistic assumptions about biomass and CCS, but less optimistic assumptions about things like batteries, about renewable integration in particular. But what we see is a relatively robust picture that emerges that even with weak policies, and especially if we go towards 1.5 degrees or well below 2 degrees scenarios, is a quite rapid decline of the carbon intensity, so the amount of CO2 emitted per megawatt hour of electricity produced. That can be relatively quickly, that can work relatively quickly in this accelerated climate policy cases, but even without much climate policy, we would expect that to decline because renewables get ever cheaper. By contrast, if you look at combustible fuels, things like gases or liquid fuels, there the carbon intensity tends actually to increase over time going forward without climate policies, because oil is getting scarce and you go to tar sands, or like you go to coal to liquid conversion processes, which are quite dirty. And even in climate policy cases, because there's limited amount of biomass, there's limited amount of hydrogen on synthetic fuels that we can deploy, it will be quite slow to reduce that carbon intensity of those combustible fuels. And that does have quite important implications for energy prices. So we all grew up in worlds where electricity tends to be the pretty expensive energy carrier on a per megawatt hour basis, whereas the direct use of fossil fuels like oil, coal or gas or oil was relatively cheap. But going forward, if you're serious about climate policy, there will be some component of regulation of fossil fuels, which also can be translated in the EU, for example. We have an explicit emission trading system, so there's a price on carbon that comes in, and that tends to increase the price of oil here, the blue colors, or gas here in this gold color, or solid carbon fuels. By contrast, if we look here in red at electricity, there we expect some increase in electricity prices during the transition to a low carbon energy system, but in the medium to long term, these electricity prices, they can decouple from the carbon prices, because we can quite readily switch to a climate neutral electricity system. And what happens then is, at some point, electricity will be cheaper on a per megawatt hour basis than liquids or solid fuels. And that's a fundamentally different world in terms of how energy systems work. So most people don't know that, but roughly, like our current energy demands, our global energy demands, only 20% of these global energy demands are currently served in the form of electricity. More than 80% of energy consumed is non-electric. And what we expect is that this will change quite drastically as we go forward, and especially so if we move to a world with strong climate policies, just because of these economic dynamics that I just described. So we are typically expecting something like 60% electrification share by 2050 in a world that's very serious about decarbonizing the energy system. And what's then quite interesting is to kind of break down this final energy demand by different sectors and different energy carriers. Apologies for this quite busy figure. But here, kind of in orange, this is kind of the electric share. You see it's very small. Right now, this roughly 20%. And we expect it to become bigger and bigger as we go forward. And the interesting question is, of course, where we come to a limit in terms of electrifying the energy system. And that's given here in these various colors, and we can go through that kind of sector by sector. So, oops, that's Yeah, sorry. So a big chunk of that's the blue part, the liquid fuels for transport. And the interesting insight here is that basically we can reduce, like in road transport, there are lots of options to go for electric mobility, which means that these remaining non-electric fuel demands in the transport sector, they are almost exclusively dominated by things like aviation, where we just need the energy density of the liquid fuels, or shipping, where it's also quite hard to go fully electric. So this is really what like a key part of the remaining non-electric fuel demands. And then if you go, sure.
So
yeah.
air, I get. So it sounds like passenger vehicles can be decarbonized, and that sounds like let's separate ships, like water shipping versus trucks, terrestrial shipping. Is that the same story or different stories?
Yeah, sorry, that was a bit quick. So actually, all of road transport is we are increasingly optimistic about this, and this is really a development of the last couple of years. That also now for trucks, it's really not a matter of if, but rather a matter of when battery electric trucks will be cheaper than diesel trucks. And the benefit, like the problem with trucks is, of course, that you need huge batteries to operate those trucks. But on the positive side, they have very high utilization rates. So they are kind of 50% of the hours of the year they are on the road. So you really have much better amortization of this high battery investment for freight trucks compared to light duty vehicles. And that's why, like, especially if you put climate policy on top, you would expect to quite quickly go into a battery electric dominated freight sector as well on the road. And that's actually, like, in Europe, that's ongoing. So it's like really the pipeline is very battery electric car dominated. In the US, for example, it will very much depend on policies. In China as well, lots of electric freight transport is in the pipeline. That's really a fast-moving sector. Maybe one last point on this: the average lifetime of a truck is significantly shorter than the average lifetime of a light-duty vehicle, which also means that the transition to battery electric freight mobility might actually overtake the transition on the light-duty vehicle side, just because the stock turnover is so quick.
Got it. And then for ships and planes, which require high energy density fuels, to what extent can you, like you mentioned, hydrogen, or it can also do methanol, ammonia, things that clean power creates, and they're just liquid batteries now for these ships. To what extent is that feasible?
Yeah, there are some experiments with electric shipping, but that's usually like really niche applications, like ferries in Norway. That's a big thing, and they only do like 5 miles. So it's very nice, but it's almost insignificant in the big picture in terms of kind of the total energy demand of the shipping sector. It's really small. So yeah, methanol is an option, but that, again, like, it's a molecule, it's not an electron that you use for the energy there. There's also experiments with ammonia, and I think the jury is still out which option will prevail. Energy density very much matters, and that's substantially lower if you go with hydrogen, so I would be a bit skeptical there. And for airplanes, again, short distances, it's plausible to go electric, but really the bulk of the energy demand and the emissions is in the medium to longer distances. And again, they are like, it's all about energy density, and there it's hard to beat kerosene. Like, even methanol has only half the energy density compared to kerosene.
Got it. Thank you.
Okay, next sector, looking into industry. That's the other big chunk in terms of residual fuel demands. And there it's basically the bulk materials that really matter. Chemicals, where you not only need the energy from the hydrocarbons, you also need the molecules from the hydrocarbons as kind of a material input, as a feedstock. Then steel making, like for steel, it's smart to go to recycled steel, but for some high quality applications, we still need primary virgin steel, and that's where we can switch to hydrogen, but that's also comes at an economic penalty and will take some time to switch there. So that's why the industry sector also has a quite a significant role here in this residual fuel demands. And then maybe lastly, can look into buildings, and buildings here includes residential, commercial, and actually also the service sector. What we expect here is a substantial increase of like the autonomous increase of electric demands, just because like the world gets richer, people have more appliances, space cooling gets more and more important. Also things like data centers that also have increased energy demand going forward. The two sectors that currently really matter for non-electric demands, that's heating, space heating, water heating, and then I mentioned and then cooking, and that's a lot in the global south. That, for example, traditional biomass is used for cooking, and there electrification is of course a straightforward option, and it's also beneficial from a co-benefit point of view. Like to take these combustion processes away from the households also has big benefits in terms of reduced air pollution. Okay, so maybe summarizing up a bit, like there's a big debate with regards to how like direct electrification, direct use of electricity in the end use sectors dominates versus these options of what we call indirect electrification. And there we think about things like converting renewable electricity to hydrogen and either using that hydrogen directly, for example, for steel making, or converting that hydrogen into like hydrocarbon fuels. So like that's something that we call synthetic fuel. So where you combine hydrogen with CO2 captured from the atmosphere into something like synthetic methane molecule, or also like synthetic longer chain hydrocarbons for liquid fuels. And what's quite useful is to think of these different types of currently non-electric energy demands. And what we did for this paper here is that we kind of ordered them from easiest in terms of electrification, like in the green colors to the left. And then on the other hand, on the right-hand side, with those sectors and activities that are hardest to electrify or even impossible to electrify. And an interesting insight is like there are quite distinct categories of activities where we can say with high confidence that direct electrification is the cheapest option. And that's road transport, that's buildings, heating, and also low temperature industrial processes. And then there's like some markets where we really know that we will need those molecules, for example, for chemical feedstocks, as I said, aviation, shipping, where we just need the energy density. And in the end, the debate about direct electrification versus indirect electrification really narrows down to this to a relatively small area of kind of in-between sectors where it's not so clear. For example, higher temperature heating processes in industry, and maybe long distance transport for heavy duty trucks. But their latest development suggested that even those end users can be served by battery electric mobility. And what's important to keep in mind is that there's a substantial difference in the overall conversion efficiency between direct and indirect electrification approaches. So think, for example, about a heating process in industry. So if you put one unit of renewable electricity into the system there, and then go through electrolysis, methanation, like convert it to hydrogen, then to methane as a synthetic fuel, and then you have like combustion process. You typically end up with around 50% of the of useful energy per energy input. By contrast, if you look at direct electrification options. There we have the benefit that we can really work in a very efficient way by using heat pumps, where you suck in ambient heat, and then because of this efficiency gain, you can convert 1 unit of renewable electricity to about 3 units of usable heat. So overall, there's a factor of 6 difference between an indirect electrification approach and a direct electrification approach. A quite similar ratio can be found if you look for road transport. There, the key difference is that a combustion engine only has around 30% efficiency, whereas an electric engine is almost 90% efficient. Okay, let's look into climate policy implications. That's an update, like a regularly updated graph from the United Nations Environmental Programme, where we can look at current trends in greenhouse gas emissions and implied emissions regarding the the climate policy plans from countries, as well as their pledges that they provided as part of the Paris Agreement. And that basically says, like, based on current policies, we expect more or less a stabilization of CO2 emissions, but not much of a decline. And that can then be contrasted with the emissions levels that we should achieve by 2030 if we want to be on track for limiting warming to 2 degrees, or if you want to limit warming to 1.5 degrees. And kind of the gap between these two developments is usually referred to as the emissions gap. And we're talking about something like 20 gigatons out of the 55 gigatons that we're currently at as a gap for 2030 emissions, and more like 25 to 30 gigatons to the 1.5 degree target in terms of 2035 emissions. And that's quite significant, and it should be an important goal for climate policy to reduce that gap. Let me show,
so just
one more
scale. You're saying 20 gigatons per decade, per year? Like, what scale are we talking about?
We are talking about 20 gigatons in 2030. So like in 2030, we should be at 33 gigatons, but we expect, based on current policies, the world to be rather at remain close to the 55. So that's
per year emissions, right?
Sure, yeah, exactly. Sorry, exactly. Like the emissions in the year 2030, yearly emissions. That's correct. Sorry.
Okay, so then, given the our slowness, to what extent are removals priority if everything else is not on track?
Removals will ultimately be required, but they will take a lot of time to scale up. So I think it's not plausible to expect like a large contribution of removals in 2030. They will be very important in 2050, 2060, 2070 to clean up the mess that we've created by then. But it will take a lot of time to get there. Just like as an order of magnitude, currently this direct air capture, like direct technical removal of CO2 from the atmosphere, we're talking about 40 kilotons per year. That's about as much CO2 as caused by one petrol station, and that's a million times, like a millionth fraction of the current emissions. So it's really like a lot of doublings that we still need to get this to a meaningful level.
So those tools are, well, highly reliable, low scale, and take time. What about things like forests or things that are short term, less reliable, but we have forests. You can kind of see sort of biochar. You can imagine those technologies scaling faster, even with they're imperfect. Yeah.
So the one thing that really is relatively fast, that's avoiding deforestation on planting trees, afforestation, and that's that can be at the level of maybe 100 megatons per year already within a couple of years, maybe even gigatons. But at the same time, because of climate change, forests get under increasing pressure. So part of that might already be offset by decay of forest systems. in the next couple of years. So that's quite uncertain, and that will still not be enough to close that 20 gigaton gap.
Got it.
We have here. Okay, I will just quickly look at this. So one thing to keep in mind is if we talk about delay or inaction, it's quite useful to think kind of a different scenario. So this is stuff that we produced more than 10 years ago. Like kind of back then, we said like this is what an optimal trajectory towards 2-degree stabilization would look like. And then we considered another scenario where you wait another 10 years before you take meaningful climate action. And yet another one where you wait until 2030 until you have meaningful action. And this is only CO2, but like we happen to be very close to the actual development here with this red curve. And what's important as a finding is that if you compare the excess emissions between this optimal trajectory and the delayed trajectories, there's two problems that we have. One is that kind of between now and 2030, we have like some excess emissions of the order of 150 gigatons by 2030. But the second, even bigger problem is that the system is not prepared to go deeper after 2030. And that's just because of kind of new coal-fired power stations that have been built because of lack of progress in learning technologies. And for example, also because of lack of progress in building up these carbon dioxide removal technologies. And like here in this diagram, that's kind of the lighter red part is like all the excess emissions that we have after 2030. If we kind of apply the same stringency of climate policy in this delayed case compared to the stringency that we would have needed in this optimal case. So basically what that means is we have to go to much greater efforts, much greater economic costs to kind of make up for these excess emissions and then reduce, like achieve deeper emission reductions from 2030 going forward, but that will be very, very difficult. Okay, I will, maybe in the interest of time, I will jump over this slide and come maybe to like one last point. What really matters is that we need to upscale like novel technologies very quickly. And this looks quite different for different technologies. Like for example, a typical number that we find is that we need 10,000 terawatt hours of renewable electricity by 2030, e.g. from photovoltaics. And we're getting quite close to that. Like we really like, if you look at the pipeline of projects, that doesn't look too bad. Electric cars, they are like 2022, the market share was roughly 10% of electric cars. What we see in these scenarios for 1.5 is something like 60 to 80% market share of kind of electric cars in new purchases, new sales of cars by 2030. That's something that we see in Norway. We are getting very close in China. We are getting close also like in the Netherlands and parts of the EU. But on the global scale, we are quite a bit behind the target. But the existence of markets where we already see that depths of penetration suggest that these goals are in principle achievable. Then there are other things like carbon capture and storage from industrial plants. I said earlier that we currently sit at roughly 50 megatons. To get to a meaningful contribution for climate change mitigation, we would need a factor of 100 upscaling by 2050. Again, that's an area where we're not on track. Or things like hydrogen. There are targets, for example, on the EU side, which imply like a 400-fold increase until 2030 relative to 2022 numbers. This is a probabilistic simulation that we did. And it looks like this is very ambitious, and we like current policies do not put us on track to get to this level. And then maybe lastly, this is kind of this direct air capture technology that I mentioned earlier. So there we're talking about 100,000-fold increase by 2050 to get to like roughly 1 gigaton per year as a contribution to climate change mitigation. That's a very steep task to get there, but it will be quite important to build up these technologies to remove CO2 from the atmosphere. Okay, so my conclusions: climate crisis is very real. So we see these real impacts. We've seen a lot of warming lately, and it won't go away, even though it's denied by an increasing number of actors. On the positive side, we have rapid technology innovation in renewables and renewable-based electrification technologies. So that emerges as kind of our best and most dominant mitigation strategy for getting anywhere close to the 1.5 or 2 degree targets formulated in the Paris Agreement. We will need substantial amount of zero carbon fuels for these hard to electrify sectors. And those account for roughly 20% of final energy demand. And the kind of key challenges for hydrogen and e-fuels is to get the costs down, to get to non-fossil carbon sources, and to really manage this upscaling task. And this is a slide that I have skipped over, but very importantly, it's important to now focus on those investments, like on the stuff that comes new into the system with substantial lifetime, and realign those investments for compatibility with these long-term climate targets. And that helps us to avoid carbon lock-ins, which will make it very difficult in the medium to long term to get emissions down. Thank you.
Well then, thank you very much. This is very interesting. I guess one thing I'd love to understand is, well, how much will it cost? I mean, what kind of global investments are we talking about, and to what extent are these public sector investments, and to what extent is it just private, like regular finance paying for things that are profitable kinds of investments?
Yeah, a typical number is several $1 trillion per year. So that's quite significant. Most of that will be covered by the private sector, as currently is already the case. It really depends. Like, the role of the government is to get the boundary conditions right, and that's where you really you have to regulate fossil fuels in some way. I think the European Union has found a quite good way of doing this with this emissions trading system, which increases the price of fossil-based energy consumption, and that to a large extent helps to kind of incentivize private investments into climate-friendly technologies. There are some areas where the government also has to invest, and that's things like hydrogen infrastructure. That will take some time, and that's quite costly to build up. We know that in some segments it will play a key role. Then there are other things in Europe. What matters a lot is kind of refurbishing buildings, switching to heat pumps. In some cases, that can be quite costly, and it does come with some social tensions, because for lower income households, it can be a very substantial burden. So again, this is where the government needs to come in to help. But like for a recent study that we did for Germany, like this share of government in investments is like 10 or 20%, no more than that. It's really like mostly a private sector task, based on like boundary conditions that are set by governmental policies.
So then what's the role of, let's say, carbon markets, cap and trade, carbon taxes, and all these kind of policy mechanisms? Yeah.
So the economic literature is quite clear that there's a symmetry between taxes and cap and trade. So really what matters is to get the price into the system. There's some asymmetry with regards to like how uncertainty is reflected in a cap and trade system versus a taxing system. But it really, like, there's not a big difference in terms of the economic effectiveness. It's really like the single most important part or like element is to get a price to carbon, and it should be in, like, at least in the medium to long term, at the order of the social cost of carbon that we talked about earlier. Like, each ton of CO2 causes a damage of $200. So like from an economic perspective, like the optimal way of dealing with this environmental damage is to also tax fossil fuels at exactly this rate of $200. And that would change a lot. Like, then that would just very quickly trigger a transition to renewable and fossil-free solutions.
Got it. Well, yeah, thank you very much. It's extremely valuable.
Thanks so much.